Hey everyone, Mr. Smith here, and in this video lesson, we're going to do an introduction to special relativity. So there'll be no practice after this lesson. It'll just be introducing you to some ideas, playing around with relative velocities a little bit, and hopefully it's having a good time. I really hope that you, before doing this, watch the NOVA documentary, Einstein's Big Idea. Minus the Michael Faraday clip that I've had in a previous lesson. It's about an hour and a half, and it's definitely worth watching. It's not mandatory viewing, but it's definitely a good intro to the next 2 days of our course. And it's entertaining, has a lot of great visuals. You learn a lot of history. So I definitely would recommend checking that out. But let's get started with the task at hand. So what I'd like to do first is to do a little bit of a diagnostic with you. So the first page of your lesson sheet, if you're following along with that in my class, has a bit of a diagnostic with, I believe, 6 or 7 relative velocity questions for you to think about. So if you want to pause the video and think about these questions and then come back when you're ready. For questions involving the speed of light later on, you can just use c. You don't have to write 300,000 meters per, or 100 million meters per second, or 3 times 10 meters per second. If you think an answer is the speed of light, you can just write c. If you think it's twice the speed of light, you can put c. So in the first question, you're thinking about why it's not necessarily accurate to say that the ball is moving at 16 meters per second in this scenario. In these later questions, you're thinking about relative velocities. So in 2 and 3, you're thinking about just kind of like everyday speeds we'd be encountering in our normal lives. And in questions 4 and 5, you're thinking about relative velocities when those velocities are getting near or equal to the speed of light. So yeah, if you want to pause the video and try those, and I'll just get myself ready here, and we'll kind of go over these. All right, so you were warned. Here we go. So let's say that Jack and Kayla are on this boat. And the boat is moving at 16 meters per second. So if you think of us being on the shore, we're watching this boat, and Jack and Kayla move by us at 16 meters per second. But what would happen if Kayla throws, let's say, rolls a ball at 1 meter per second relative to Jack? So on the deck, rolls the ball towards Jack, and as far as she's concerned, it's moving to him at 1 meter per second. Well, what we would see this relative velocity, and I'm not going to use any formal equation here, just going to, like, common sense would say, well, the boat's moving at 16 meters per second, and on that boat, the ball is moving an additional 1 meter per second. So I would see the ball moving at 17 meters per second. And if Kayla rolled it at 2 meters per second relative to her, it'd be 18, and so on and so forth. And so what I've kind of done in this question is just I've added those two velocities together in a very simplified way. So this is the idea for the next several diagnostic questions. If you want to pause it and then actually go back at those just by using V1, V relative equals V1 plus V2, you can. So if I'm riding a motorcycle at 15 meters per second, and I throw a ball off the front at 5 meters per second, again, relative to me, somebody watching this from the street would see the bike going past an additional 5 meters per second of me throwing it off the bike, and it would be 20 meters per second, like the Jack and Kayla question. For number 3, if I throw it backwards, it would be 15 minus 5. I'd still see the ball traveling forward, but at 20 meters per second. Now let's talk about what happens if these speeds get close to the speed of light. So I'm traveling very fast, half the speed of light. And I turn, instead of throwing a ball, I'm now turning on my headlight. So it's not a ball that's moving in front of my bike. It's now light itself. If I answered the question 4A, like I did question 2, and just add those together, so my anticipation is that some of you guys wrote 1.5 times the speed of light, but you'd be wrong. What speed do you measure the speed of light coming from? You would just see it moving at c. Excuse me, I think most of you guys would have said 1.5 c for the next one. But yeah, we see the light moving at the speed of light, but the stationary observer, unlike the balls adding together, where I see a ball on my bike moving forward at 5 meters per second, the person on the street sees 20 meters per second, we're both going to see the speed of light traveling at the speed of light. So things get interesting when we talk about speeds near the speed of light. We need ways to handle that. If you shine the flashlight off the back of your bike, you're going to see it traveling at the speed of light, and the stationary observer will measure it traveling at the speed of light. So I'm not going to be doing speed of light. Unlike question 3, I won't do 0.5 c minus c and get half the speed of light in the other direction. No, we're all going to see this light traveling at the same speed. So we need ways to kind of account for this, because doesn't really fit into our kind of classical mechanics, the way we've been doing things. And I asked you a sixth question here. Do you think it's possible for you to catch up to a beam of light? Do you think it's possible to provide enough energy to accelerate some object like you up to the speed of light? And although it's possible to get very, very close, you can't actually reach the speed of light. You can get closer and closer and closer and closer, but you'll never be able to travel at the speed of light. And later on today, we'll actually talk about, well, if you keep pumping energy into a system to try to accelerate an object, let's say, and you're accelerating and that object is getting faster and faster, but you just keep bumping up against the speed of light, where does that energy go? Well, we're actually going to talk about where that energy goes, and there's an interesting idea there. So with that little warm-up in the books, talking about relative velocities and how, with a simple case of a bike and a ball, yeah, we can just add those two speeds together or subtract, but we can't do that with light. So this brings us to relativity theory. So I'd actually recommend that you just actually take a pause and just maybe with your phone, just snap the QR code there and watch a 2 or 3 minute video on relativity theory by Minute Physics. Definitely worthwhile, and it actually motivates what we're doing next. So if you want to pause and do that, that'd be great. And unpause when you're ready. But let's move forward. So what we're looking at today is relativity theory. So we're analyzing the properties of objects traveling, that should be near the speed of light. And we're going to see very interesting things happen. So as I mentioned, watch a short video from Minute Physics about relativity theory. It's enjoyable, it's quick, learn something new, but then we're going to apply that in our next slide. So I'm going to assume that you guys have watched the video and have seen the following equation. So when we're adding velocities and doing relative velocity when the speeds are near the speed of light, and actually this is true all the time, it's just that for low speeds it's just not noticeable. We just can't add speeds in a linear fashion like v1 plus v2. You guys would have saw in the video, there's actually a more refined way to add velocities together when your system has like an upper limit. And that equation was relative velocity equals v1 plus v2, but you divide by this factor, 1 plus v1 v2 over c squared. And what this does, it allows you to add relative velocities where you have an upper limit for velocity. And in this case, the upper limit is c, the speed of light. And let's just play around with this and just show you that it works. So let's look what happens when we have very low speeds, right? Let's say v1 is 15 meters per second. Let's say it's like the bike example, the first bike example, and v2 is 5 meters per second. So let's plug our stuff in here. So we get 15 plus 5 over 1 plus 15 times 5 divided by c squared. So punch that into your calculator and see what you get. Now, on my standard calculator, I believe I'm just going to get 20. That's my guess, but let's see. My calculator just gave me 20. It can't even tell the difference between this number and 20. Now, if you tried it on a phone, or maybe like an Android or iPhone, I wonder if you might get 19.9. The idea is it's so close to 20. It's like 19.99 with like so many zeros meters per second that it's basically 20 meters per second. So at those low speeds, yeah, the relative velocities, we just add them together like it's 20 meters per second. Let's look at a second example. Let's try this. So let's say I'm riding my bike at 15 meters per second, but now instead of throwing a baseball, I turn on my headlights. And so instead of throwing a ball at 5 meters per second, I'm turning on my headlights and the light's going at the speed of light c. How does this equation work? Let's check it out. Because what we should get is like somebody on the street should see it moving at the speed of light. I should get exactly c using this equation. So let's actually try it. So we have 15 plus c over 1 plus 15 times c over c squared. Guys, check this out. So we get 15 plus c. On the bottom, we have 1 plus and then 15c divided by c squared. That's 15 over c. If I multiply the top and bottom by c, I get c times 15 plus c. And on the bottom, 1 times c is c. C times 15 over c is 15. And 15 plus c and c plus 15 are the same thing. We actually get c. We get that upper limit. So isn't that cool? Let's try one more example just for fun. So let's say that your bike could somehow travel at half the speed of light, and then you shined your light, whatever, at headlight at c. Do you still get c? Does someone on the street still see the light moving at c? Well, it should. So let's try this. So we have v1 is 0.5 c plus c all over 1 plus 0.5 c times c over c squared. So on the top, you just get 1.5 c. Those are like terms. On the bottom, we're going to get c times c is c squared over c squared. Those actually divide out. 1 plus 0.5 is 1.5. And look, those divide out, we get c again. So hopefully you're convinced that this formula gives you the relative velocity for geometries where you have some upper limit to what you're adding. So that's really cool. In this case, the upper limit is for the speed of an object, which is c. So anyway, that's pretty cool. First little dive into relativity theory. This idea has consequences that things traveling near the speed of light might not necessarily fit into our classical view of like Newtonian mechanics. We might have to update a few things. So until the 1900s, all physics was considered to be classical. So basically, follow Newton's laws was deterministic. If you knew the initial conditions, like, you fire this cannonball with a certain angle at a certain speed, and you know all the properties of the air resistance, you could fully determine the outcome. And people thought that physics was done. Like, we have described the universe. All we need to do is just get more decimal places, get our constants to be more precise. But as we're going to see over the next few days, that just got all blown apart with quantum theory and special relativity and general relativity. It revolutionized how we think about science and philosophy. And instead of the world working deterministically, the world actually works probabilistically. I think I said that right. Probabilistically, yeah. And events that are thought to occur at the same time in one reference frame did not in another. And this was kind of the birth of modern physics. So we're actually going to look at one of Einstein's thought experiments, and he had a lot of these. So in German, that's a Gedanken experiment, but we're going to call it a thought experiment. So what is a thought experiment? An experiment that is hypothetical, where questions arise but not necessarily answers. So one of Einstein's thought experiments was the following one regarding a train on a set of tracks. One observer is in the train and another is outside the train, and the train has no windows. So just as an aside, if the train has no windows, then the person inside, they can't tell if they're moving or not. As long as the train's moving at a constant speed, so with no acceleration, that person is just going to feel, is not going to feel anything. You know, if the train was accelerating, they might feel a force and fly back or something like that. But and this might take you some time to wrap your mind around. But if the train is totally dark, there's no windows, and it's moving at a constant speed, you can't actually tell if it's moving or not. There's no way to tell. But we're saying it's traveling fast and has, you know, sophisticated enough electronics that it can measure the distances in time we're talking about. And we're looking at two cases. We're looking at when the train is stationary, and we're looking at when the train is moving close to the speed of light. Excuse me. And what we're going to look at is in each of those cases, what happens when lightning strikes the front and back of the train at the same time. What would the observer in the train see? And what would the observer outside the train see? Now, if you want to pause and check out this short 2-minute illustration of this idea, it will help it sink home and you can see the result. And then we'll just try to get down those results onto paper. So yeah, this is like, it looks like somebody programmed it from the 2000s, but it's a good visual. So just enjoy it and unpause when you're ready. I'm going to move on. So I'm going to assume that you guys have watched the video and are ready to kind of discuss the two cases here. So in this case, the speed of the train is 0. And when I have on this diagram, OM is just referring to the observer in the train. Kind of moving with respect to the person outside the train. OS, that's my observer outside the train, maybe the stationary observer for S. So what happens when the train's at rest? So lightning strikes at each spot, and the light takes a certain amount of time to reach each observer. But you can see due to the symmetry, because the train is at rest, you know, the light travels the same distance, same time, same speed. Both observers are going to see the lightning strike at the same time. So OM and OS see the strikes at the same time. Do I want to add anything to that? I mentioned this, but I'll just get it down. The light travels the same distance at the same speed, right? So nothing really crazy going on there. Let's look at the second case. So in the second case, the train's moving close to the speed of light. So the following would hold for the train traveling at any speed, but we're going to have it moving close to the speed of light, so the observers can see something drastically different. So, diagram. So let's first of all think about from the stationary observer. So I'm going to use my old dark blue color for that. So the light from the lightning strike at A and the light from the lightning strike at B travels the same distance in the same time. And for this observer, nothing has changed. OS, the lightning strikes, says the lightning strikes are simultaneous, happen at the same time. Lightning, there we go. The lightning strikes are simultaneous. But what does the moving observer see? So I'm going to switch to maybe red here. So the lightning strike from A, so travels at the same speed, but while the light is traveling forward here, the train is also moving forward. And so what happens is the light has to travel a little bit farther before reaching the moving observer. And the strike from B, lightning strike happens, and the light starts moving. But here, the moving observer is moving closer to the strike, so the strike doesn't have to travel as far before reaching the moving observer. So what would the moving observer conclude? Well, this light traveling at the speed c only had to travel a shorter distance to reach him. It's going to appear there faster than the lightning strike moving at the same speed, covering a longer distance. The moving observer is going to see the strike from B happening first, and that moving observer will conclude that they didn't happen simultaneously. He's going to conclude the lightning strike at B happened first. So the light from B arrives before A. And so his conclusion is that the lightning strike at B happens first. And who is right? Well, they're both right. In the stationary observer's frame of reference, they happen simultaneously. The moving observer saw them happen not at the same time. The light from B happened before A. And, as far as the moving observer is concerned, this train's blacked out. There's no windows. They're not moving at all. So they would say that, lightning strike B happened first. And both of them are right in their frames of reference. So result that, and hopefully you're convinced at this point, the events that are simultaneous in one frame of reference are not necessarily simultaneous in another. So we just kind of showed that. Anything else here? Yeah, it depends on the relative speeds of the observers. So what we have to do in our next lesson is try to quantify that, well, if two events aren't simultaneous and times between events is kind of up in the air, how do we quantify that based on how fast they're traveling? So that'll be our goal in our next lesson. And Einstein brought two postulates to the table to kind of make sense of all this. So the first is that all laws of physics are valid in all inertial reference frames. So what do I mean by that? Or what did he mean by that? I'm just going to give you a quick example here. And I think I have space. Yeah, I have space at the bottom here, so I'll do that. So consider somebody in the flatbed of a truck. And the truck is at rest. And the person in the truck, it's a big person, is holding a ball, and he drops the ball. What are we going to see as somebody standing on the side of the road? If the truck's at rest, we just see the ball dropping straight down, right? And we're like, hey, no big deal. That's just Newtonian mechanics. You drop the ball, acceleration of gravity brings it down. But what would we see if the truck instead is moving with some speed greater than 0? So what we would see, so the person in the truck would see the ball going straight down. But for us on the side of the road, it's like the ball is dropped with some horizontal initial velocity. And what we would see is that accelerating down due to gravity, but moving right with the constant speed of the truck. But what we would just say is like, oh, nothing's weird here. This is just Newtonian mechanics. I see the ball as a projectile with some initial horizontal velocity, and it's just behaving like a projectile. Everything is making sense to both me outside and the person inside who just sees it dropping. Because those are inertial reference frames where the laws of physics hold. They're not accelerating. They're both traveling at a constant speed, v equals 0, v greater than 0. So all laws of physics are valid in all inertial reference frames. And that light travels through empty space at the same speed. And this is, it's so close to 300 million meters per second that we just normally use it. Later on, we might, when we get very precise with our nuclear physics, we might use an updated version of that. But it moves at the same speed relative to all inertial frames of reference. So somebody, the truck moving, the truck's at rest, the truck moving, a person biking at 50 meters per second at half the speed of light, as long as they're traveling at a constant speed, so they're at in an inertial frame of reference, they're going to see light traveling at the same speed. And this has consequences. As light travels at the same speed, we just saw there's consequences with the lightning strike example. Two people can have two valid observations that are different, and they're both correct. So we need to quantify this. So there's consequences in terms of time, in terms of lengths, and in terms of momentum and mass and energy. And we're going to start investigating those in our next lesson. But that's next up. So guys, for now, no practice with this. If you just want to take a break and digest these heady concepts, that's totally cool. But I do recommend that you go back, and if you have time, even if you're just chilling tonight and want something to watch, PBS Nova, Einstein's Big Idea, you won't regret it. All right, guys, I'm signing off for now. Hope you're having a good day. Stay well. We'll see you soon.